All right, so we are into section 16.2. We're going to have an A and a B. So this is 16.2A. 16.2 is about what's called line integrals. I have to admit, when I was first doing this back when I was in college, I did not understand the concept. I was like, why am I taking the integral over a line? But that's not what it actually means. A line integral actually means that we are using line segments or tiny little line segments to actually do an integral. So let me kind of give you an example, a graphical example here of what we mean. So you're going to have some kind of a curve, and this will just be a two-dimensional example here, but it's actually a lot easier to do in 3 dimensions, but I'll start off here. So if there's some kind of a curve, whatever this curve does. Now this one obviously could be defined as an actual function, but it also could be defined parametrically. And really what we're going to be doing is doing most of these parametrically. Now this is the hard part. You're going to have some kind of a curve which basically comes off of the page. So I know this is going to be drawn a little bit differently, but if this was a curve that was basically above, like actually physically on the z-axis above the curve, then what you would have is you would have some kind of a distance which comes down. Oops, that's supposed to be a different color, sorry. Some kind of a distance which comes down here, some kind of a distance which meets here, a slightly different distance here. And again, what you have to think of is these things are kind of, it's 3-dimensional. I'll do a better sketch of this on the next page. But basically what we're doing is we are taking an integral where the black part is what's the projection down into the xy plane underneath of the green curve. So the green part is the actual curve that we're taking the line integral of. And to do this, we have to have there's two parts. One is that you have to have a curve C, and we are going to label the green part, that is C. And it can be defined as some kind of a function of x, or it can be defined parametrically, which is actually the way we're going to do these things. And so we would have x being some function of t, and y is going to be defined as some function of t. And then the second thing that we need to have is we need to have our f of xy. So again, this is our green curve. Our f of xy has to be defined over C, or over the curve. In other words, there can't be any undefined values through there. It's got to be defined the whole way. So, I don't know what our curve is here. But we could say that, f of xy in this case would be something like, 3x plus 2y. That's probably not what that curve is, but we could say that. And if you look at that, there's nothing that makes that undefined. So you would have a defined function of xy over the curve. All right, let's go on to the second page, because I think this is going to be easier to kind of get a general idea of what's going on. So what you can see is that this is a pulled straight from a book. It kind of looks like a ribbon, where the ribbon starts off as being very tall the closer we are to the origin, and then the further you get away from the origin and this thing kind of starts to wind its way through, the ribbon gets smaller and smaller, because the curve itself starts very high on the z values and starts to come down here in red, and it starts to come down and get closer and closer and closer to the xy plane. So that in red right there would be basically like your function of xy. The C part that you see on the bottom there, this is what the curve is over top of, and this is the projection down into the xy plane. And it comes around there like that. So that's the projection down into the xy plane. So ultimately, this starting point right here would be like t equals 1. And then this finishing point over here might be like t equals 2. So you're going to take this from t equals 1 to t equals 2. So what is it exactly we're doing? This is what I meant by the line segment part. So if I wanted to go from, well, we're not going to do it from t equals 1 to t equals 2 here, but if I wanted to start here, let's go in orange, and I wanted to create a small little line segment, well, that part of that's too big. Let's try and do this a little bit smaller. So maybe like, nope, don't like this drawing. Hold on, getting there. Something like that, maybe. Yeah, I'm not doing a very good job here, and I apologize. It's because I'm not making my base thick enough here. So there we got a base. All right, closer. That's much better. All right, so what you can see is the hypotenuse of that triangle that I've created, it's got some kind of a change of x. I did not draw it very good because it should have stayed parallel. I'm going to try one more time here. There we go. That's better. Change of y, and then a change. Okay, there we go. So we've got some kind of a, right here, that's a delta x. Right here is a delta y. And if we were to find the hypotenuse of that triangle, that would be a line segment which closely approximates the length of the green curve. Well, obviously, the smaller and smaller and smaller we make those triangles, the closer the approximation is, or the closer our line segments based upon the hypotenuse of these triangles is going to approximate or become basically the curve. So now let's go back to a general idea of integrals. If we have some kind of a curve, whatever the curve looks like, and this is maybe our curve that we've got on this particular problem, f of x, y, and it is coming down. If we look at where it starts to where it finishes, we can definitely see the difference in the height. But the key is, if we break this into those little thin ribbon strips that you see there, and make those infinitely thin. Now I'm just, obviously this is going to be much bigger so we can get some kind of a detailed drawing here. But if we make these infinitely thin, the distance in between those things is going to be ds, which is the change of a arc length, where s is the arc length. So if I'm going to take an integral over that curve, and that's how you define this, it's a big integral over c, so over the curve of my function of x, y. The question is, what goes out here? Well, because I want to do this with respect to the arc length, okay, I want those little segments to be basically arc length segments. We're going to have to put this into parametric form. So we're going to go from t equals 1 to t equals 2 of some kind of a function of x of t, y of t, ds. But if you remember, and this is going back a little bit, s itself, again, represents the arc length of a curve, and that's in parametric. So what was the arc length of a curve? Well, the arc length of a curve, remember just looking at our little orange triangle down there, it's the change of x squared plus the change of y squared, take the square root. It's the Pythagorean theorem of the rates of change. So our ds, I'm sorry, not our ds, just our s, our arc length is dx over dt squared plus dy over dt squared, take the square root. Okay, that's the hypotenuse of the triangle. So then s of t, so s as a function of t would be the same thing as the integral from 0 to t, the square root dx over dt squared plus dy over dt squared dt. Where ds over dt itself is just going to be, again, this integral right here. If I take, probably should have written this in a different order, but either way, it's okay. Question might be, how am I getting to this integral right there? So I'll change colors here and I'll just put this. So ds over dt is this square root plus dy over dt squared. And then if I simply multiply both sides by dt, you would get that ds is, once again, this particular square root times dt. So ultimately, what we get out of this, after all this confusion, and I apologize if it is confusing, is you get that the line integral over c of f of x of t, y of t, because it has to be parametrically defined, ds, is equal to the integral from t1 to t2 of f of x of t, y of t, there's your parametrically defined function, times ds, which is nothing more than dx over dt squared plus dy over dt squared dt. So that's the equation that we're going to have to do a line integral. And what the line integral gives, again, let's go back up to the sketch. The line integral really gives, you would probably say the easiest thing to say is the area of that two-dimensional ribbon. So again, I want to kind of I'm trying to do my best to explain this three-dimensionally. So we have found the volume underneath of a surface, as long as it's defined over a domain. Well, now what we're trying to do is we are literally trying to find the area beneath a single curve. Okay, not an entire surface, just a single curve, which is that red one right there. We are trying to find the area that is covered underneath of that single curve between that and the xy plane in this case. So over top of some kind of a defined curve in the xy plane. So we are basically trying to find the area of that ribbon, as opposed to the entire volume of something under a whole surface. That's kind of the goal of doing a line integral. All right, we'll probably do about 2 examples on this one, then we'll come back with another video. So let's see how this works. We want to evaluate the line integral, and I know it's a line integral because it's an integral over c of 2 plus x squared y ds, where c is defined to be the upper half of the unit circle, x squared plus y squared equals 1. Okay, so whatever this thing looks like when I project it down into the xy plane, the projection is going to be the upper half of a circle, x squared plus y squared equals 1, which means you have a radius of 1 in either direction. Now again, whatever this 2 plus x squared y does, and I'm going to try and again redraw this, this is going to have some kind of, this is not straight up on the y-axis, this is coming off of the page. You know, it's going to do whatever this is going to do all over this thing. It's too hard to draw from this perspective. So let me go ahead and kind of sketch this thing three-dimensionally. And because it's extending on the x-axis, I'll go that way. So I know that it's going to look something like this projected onto the xy plane. Okay, and that's -1, that's +1. Whatever this curve does, it extends vertically up off the page. Now let's try and figure out actually what this thing does, and then I'll try and sketch it. Given the fact that this thing says it's part of a unit circle in the projection, To me, the easiest parametric to do would be polar. Okay, we probably want to go ahead and put this into polar coordinates. So we're going to define x parametrically as cosine of t, because x is cosine t. Y we're going to define as sine t. Now, given the fact that the radius is 1, because technically it's x equals r cosine t, and then y equals r sine t, the fact that the radius is 1, I don't have to put the r in front, the 1 in front of that. If this circle had been a circle of radius 4, then I would have x equals 4 cosine t, y equals 4 sine t. Hopefully that makes sense. So we'll define it parametrically. So when we take our integral for the line integral, we need to figure out the bounds. Well, it's going to go from here to there, which in polar is going to be from 0, an angle of 0, out to an angle of pi. It's going to rotate from 0 to pi. I'm going to erase that here, but I just wanted to show you that that's where the rotation was. Whoops. I'm erasing the wrong stuff. I'm trying to get those arrows erased. There we go. So 0 to pi. Okay, I have to redefine my function, which is 2 plus x squared y parametrically. Well, 2 is just 2. X is cosine, so it's going to be cosine squared t. Y is sine, so that's going to be sine t. ds. But then we need to figure out what ds is. Well, ds is, in this case, dx over dt squared plus dy over dt squared, take the square root. So the derivative, let's write this down just so we'll write it down separately. ds is going to be the square root of the derivative of the x part squared. The derivative of cosine is negative sine squared. The derivative of the y part, which is sine of t, is cosine t squared dt. But the nice thing about that is, in this case, sine squared plus cosine squared is 1. Take the square root of that, it's still 1. So really, all of that equals 1 dt. If you can simplify, please simplify. It makes it a lot easier. So we're going to have an integral from 0 to pi of 2 plus cosine squared t sine t times our ds, which is just 1 dt. All right, so technically, to do this integration here, we would probably want to go ahead and separate it. I think we can probably get away with not doing the separation here, as long as you realize that this part, when you do separate it, you're going to have to do a u substitution. So for the part in red here, we would have to let u be cosine t. That means du is going to be negative sine t dt. And then dt would equal du over negative sine t. So maybe we will write this as two separate things. We'll see. Let's do the integral then. We'll split it up. So we'll do the integral from 0 to pi of 2 dt plus the new integral is going to be, let's see, u squared sine t times our new dt, which is du over negative sine t. Sines are going to go away. The negative can get pulled out. I'm going to go ahead and change the bounds on this one since I went ahead and split it up anyway. So if I plug in 0 for cosine of t, I'm going to get 1. So that's my new lower bound. If I plug in pi, we're going to get negative 1. So that's the upper bound. So then we're going to have the integral from 0 to pi of 2 dt. If I pull the negative out to the front, my bounds are still upside down, so I can get rid of the negative by flipping the bounds. So I'm going to keep this a positive, but I'm going to flip the bounds. And now all I have left to integrate is u squared du. Properties of integrals there. So let's see what we ultimately get here. So the antiderivative of 2 with respect to t is 2t from 0 to pi, plus antiderivative of u is u squared is 1/3 u cubed from -1 to 1. So plugging in the first stuff there, we're going to get 2 pi minus 0, which is 2 pi. The second one, we're going to get 1/3 minus -1/3, which is 2/3. So we ultimately get 2 pi plus 2/3. So that's basically going to be the area of that ribbon over top of the curve C. Now, what exactly this looks like, kind of hard to tell, but considering that this is basically in parametric some kind of a sine and cosine curve, it's going to look kind of like a sine or cosine curve. We could actually figure out the exact values if we wanted to, but ultimately I think it's going to do something like this, where it does something like that around the curve. It's going to go up and down, varying in different heights. And you really could figure those out. We could plug all that stuff back into the original z value and figure it out, but I'm pretty sure it does something like that. Not that that's extremely important to know the shape of it, but we did find the area of that ribbon which surrounds that curve here, C. So that's what it was that we were looking for. All right, I think I'm actually going to go ahead and stop this video right here, and we'll come back with another one. This might be a 3-video lesson because these problems can take a little bit longer, although I'll try and go through some of the next few problems a little bit quicker.